And we're doing chapter 2, motion in one dimension. Okay, I think we need to, let me switch this to draw. Okay, so motion in one dimension, okay? And then in this chapter, we focus on the topic of kinematics, which is how to describe a motion. Well, in later chapter, we'll do dynamics, meaning explaining a motion, okay? So we focus on one-dimensional motion, and we developed a bunch of quantities to describe motion, like time, displacement, velocity, and acceleration, okay? And we kind of went through their physical meanings and using examples and everything. And most of these quantities are vectors, meaning they have both magnitude and direction, okay? So, well, the scalars are the quantities that only have magnitude, like time. And these quantities can be organized kind of like by considering a quantity, and then it's the changing rate, meaning that take the change of the quantity divided by change of time, and then another changing rate, okay? And then we talk about the space-time diagram that we sometimes use to do calculations to show the motion. And we also did, okay, so yesterday we talked about instantaneous velocity. And as we said, this is basically just essentially we just use a really short time interval for instantaneous velocity. And then we talk about we give the example of doing, solving a problem. And as I said, there's basically, to solve a problem, you can either start from what is given the problem to what is you want to find out, or you start from what you want to find out, go back or connect with what you're given. But it's important to write, it's a good habit to write everything down, you know, like draw a picture, draw a graph, and then write every quantity that you're given in there together explicitly. This can help you solve the problem, okay? And yeah, there's some couple other ways to solve problem, like divide and conquer and then simplification, okay? And then we did this exercise together, right? So that's where we left in yesterday's lecture. So today we'll let's continue. So we'll talk about the second part of this chapter. The second part cares about specific kind of motion. And certainly, as always, like a rule, we'll start from some simple motions. We'll do some simple motions, okay? So again, remember, we're talking about one-dimensional motion, right? So something moving on a straight line. Now, what is the simplest motion you can imagine for one-dimensional motion? If you have something moving on a straight line, what is the simplest possible motion that you can have?
Forwards and backwards.
Yeah, there's yeah, but you can say, okay, yeah, see, first of all, right, this thing definitely can move forward or backward, right? So in general, the motion could be involving both of these two directions. You can go this way a little bit and then going back a little bit and then going forward again. So certainly a simple case would be it only goes one direction, right? So for example, let's say going to the forward all the time, right? That's certainly simpler than going both directions, okay? Now let's consider all the possible motions going forward, okay? Now what is the simplest motion you can have for something going forward? Oh, okay, so I got some message, okay. Oh, that's okay. Yeah, somebody said she has a connecting problem. That's okay, just take your time. So, well, the simplest, again, the simplest meaning that there's not much change of the motion, right? The motion is like a very simple to describe. Well, it turns out the simplest motion you can have is constant velocity motion, okay? Now you may say something at rest is simpler, even simpler than that. Make sure this is select, okay? So that's probably the simplest possible motion, but this is a trivial motion because you do not move at all, right? So it's just a special case. So we don't need to, we don't talk about this one, okay? The simplest non-trivial motion is a constant velocity motion. Okay, so again, by definition, by this the name, right? So what it means here is something moving forward. See, because of constant velocity and velocity is a vector, so that means if velocity is constant, then both the direction and magnitude does not change. So if you move forward, you always move forward. Okay. Now it also means that you move forward with constant speed. Okay. So it's a kind of a, it's like you're driving on the road with constant speed and going forward. Like sometimes if you travel to like a long distance, right? You go to interstate. That's sometimes what happens, right? You drive on the state on the interstate highway. You just keep the same constant. You even can use this cruise control. So it's that kind of motion, constant velocity motion. Okay. Now what can we say about this motion? This motion actually is pretty simple because by definition v is constant. Okay. We'll write v equal to constant. Okay. So what it means here is if we use the basic definition of v, right, like a v average equal to delta x over delta t. But in this case, this is just a constant number. So you can easily calculate delta x equals to v times delta t, right? If you know this value of the velocity, you can use this to calculate the displacement, okay, given the time interval. Or you can use the time interval. I mean, you can use the displacement to and the velocity to figure out the time interval. So either one of these three, I mean, this is essentially the same formula, all come from this formula, but this is the basic formula for constant velocity motion. And if you know two of these three quantities, you can calculate the third one, okay? Actually, the example and exercise we did yesterday was actually kind of constant velocity motion. It's not totally constant. See, in this case, right, this part is constant, this part is constant velocity, but the whole motion is not constant. But still, if you break down for these part of motions, they are constant velocity motions, and you can use the formulas to get the corresponding quantity. Okay, same thing here. For the exercise, they both move with constant velocity. Okay, although they're going opposite directions. So again, we're using these kind of equation for that. So there's really not much to talk about. So I think that's all we want to talk about for constant velocity motion. Okay, so let's move on to the next one. Okay, so what is the next simple let me separate, like simple motion that you have? Okay, what do you guys think? After constant velocity motion, what is the second simple 1D motion we can talk about? I guess this kind of question maybe is a little challenging to you guys, but okay. So the second is actually, okay, see, let's say now let's allow the velocity to change. Okay, so it's not going to be constant velocity anymore. Okay, it's going to be changing velocity. Okay, that means there's going to be acceleration, right? But out of all the possible cases of changing velocity, the simplest one would be the velocity changing with constant rate. So we will talk about constant acceleration motion. Okay. Okay, so constant acceleration motion. Okay, so now what can we talk about there? Okay, let's first try to derive some formulas that we can use to study this motion, and then we'll give some examples of the. So basically, as we see here, right, the acceleration is constant. So let's start from here. A equals to a constant number, right? So what does that tell you? So certainly we have, by definition, we have A equal delta V over delta T, right? Now for A is constant, we can do delta V equal to A times delta T, right? Now sometimes we will write this as V final minus V initial, okay? Again, I'm just deriving this. All these are kind of a consequence of this basic definition. So we would write sometimes like this: V final equals to V initial plus A delta T. Okay. So this is kind of like one of the formulas we can use to talk about constant acceleration motion. Okay. Okay, now this is nice. However, a lot of cases we're interested in still the displacement, okay? Like this one, okay? So we like to have a formula to calculate displacement, okay? So let me write down this, okay? Again, based on the definition of average velocity, we have like this. But the question, can we use this formula directly in constant acceleration motion? What do you guys think? Again, send me a message, either yes or no. Can we use this formula directly to calculate the displacement? Somebody says yes, yes, yeah, yes, okay. Yes, okay. Now the answer is actually no, okay? We cannot, okay? Why? Think about it, right? Let's say you want to try to calculate displacement, okay? Now the question is, what v should we put here, okay? Remember, v is changing, v is keep changing, right? V is not constant, v is changing all the time. So, what v should you plug in here, right? That's not clear at all, right? Well, certainly you don't want to use the initial velocity here because the final velocity is different from the initial, right? The initial velocity is only there for like a single moment. So same thing, you cannot use final velocity either. So it's really not clear what we plug in here, okay? So we want to really use this formula, we have to use the actual average velocity, okay? To calculate. Well, this average velocity is not v initial or neither v initial or v final, okay? Actually, for constant velocity motion, v average can be written as a very simple combination of the two. It actually equals vi plus vf divided by 2. So that's our average velocity, okay? Now, where does this come from? Okay, it's kind of a little bit hard to explain without using some sophisticated mathematical tool, but from an example, let's say, right, because v change with constant rate, right, because a is constant, right? So you could imagine, like, if you break down your time like into many small slides of 1 second, let's say 1 second, 1 second, 1 second. This is your time, okay? It's time. And then your velocity is gonna, in every single second, it's gonna change the same amount. You know, if you start from, let's say, 1 meter per second, then you become, maybe let me put meter per second here. Okay, let's save some space. So it becomes 2, and then 3, and then 4, and then 5, and 6, 6, and 7, and 8. That'll be like, okay, let's keep it. That'll be like one way of changing velocity, you know. Now, if you add all these, let's for simplicity, let's assume that during the second is same velocity. So that if you calculate the total displacement here, okay, 1, 2, 1, 2, 3, 4, 5, 6, 7. Okay, if you calculate these, maybe let me put 8 as well, just for simplicity here. So another one, 8. So if you calculate this total displacement travel during all this time, so this one here will be like 1. This one here will be 2. This one is 3 and 4 and 5 and 6 and 7 and 8. Right? Just multiply the velocity by the time. So you add them together, right? This is the total displacement. Okay. You add them together. This give you 9, another 9. So you have 4 9s. So it give you 36. Okay. So what I meant is 1 plus 8 is 9, 2 plus 7 is 9, 3 plus 6 9, 4 plus 5 is 9. So together is 36. Okay, meter. But so the average velocity, if you calculate using delta x over delta t here, is going to be 36 divided by 8. So you have well, that's so okay, this is gonna be 4.5, okay, meter per second. Okay, well, you can check if you take the initial velocity and final velocity divided by 2, you have 1 meter per second plus 8 meter per second divided by 2. You get also 4.5 meter per second. So from this, you can kind of see that this formula works. Okay, I want to emphasize this only works for constant acceleration motion. It does not work for other motion in general. It's just the specific property of the constant acceleration motion. Okay. Now suppose you got this one, right? Now how do we calculate delta x then? We would write delta x as vi plus vf divided by 2 times delta t. Okay, so that's our second formula here. Okay, for constant acceleration motion. That's how you calculate the displacement if you know the initial velocity and final velocity and time. Okay. Well, sometimes you do not know the initial, the final velocity. You only know the acceleration. So if you plug 1 into 2, you can get a new formula. Plug 1, formula 1 to 2. So you have delta x equals to vi divided by 2. Okay, so vf here using the formula 1 is vi plus a delta t. So it's going to be vi plus a delta t. Okay, times delta t. Okay, so together you have 2 vi plus a delta t over 2 times delta t. Okay, now if you want to now kind of get rid of the fraction by dividing 2 on both these two terms, you get the first term here, 2 divided by 2 is 1. So you have vi times delta t. And the second term here will be 1/2 a and delta t. So delta t squared. So that's going to be our third formula here, okay? That by plugging the first formula to the second formula, okay? Got our first formula, third formula. Okay, now another useful formula is sometimes you do not know anything about time. You just want to, but you know initial and final velocity, okay? And in that case, you can get rid of time and get another formula. So for that, we still plug the formula 1 to formula 2, but we plug it a little bit differently, okay? So from formula 1, we have vf equal to vi plus a delta t. But that means if you subtract vi on both sides, right? So and then divide by 8, that means delta t equals to vf minus vi divided by a. Okay, so that's like a that you can express the time interval as the ratio of this and this. Okay, now if you plug this to 2, we got another formula. Okay, delta x equals to okay, remember this one here is vi plus vf divided by 2 times delta t. So vi plus vf divided by 2 times this. So it's vf minus vi divided by a. Okay, so you multiply these together, you have actually 2a in the denominator. So vi plus vf plus vi times vf minus vi is just vf squared minus vi squared. Okay, now you can multiply this by yourself. It's pretty easy. Just you got 4 terms, some term cancel out, so left is this term. Okay, so that's our fourth formula. Okay. Now, what I want to emphasize here, you guys do not need to know how to derive those formulas. Okay, for some of you, this all kind of symbols may look like you know, crazy, complicated. You know, however, I do want you to know the existence of these four formulas, and I want you to be able to use them to solve problems. Okay, these are sometimes called kinematic formulas of constant acceleration motion. Okay. So, and as you see here, they're not totally independent. Okay. So essentially, this formula is the independent. I mean, and then the first and the second formula are kind of most fundamental ones based on our derivation. Oh, I got a message here. Let's see. Constant velocity means zero acceleration. Oh, yeah. Yeah, somebody is saying that constant velocity motion means zero acceleration. So that's constant. You're right. So in some sense, constant velocity motion is a special case of constant acceleration motion, while the acceleration is zero. But that case, again, kind of trivial. So so normally when we say constant acceleration motion, we mean the acceleration that's not zero. Same thing like this one, right? At rest, you can consider this as a special case of constant velocity motion, but it's not very interesting. So anyway, hope this answers the question. Oh, I got another message. Okay, that's good. So basically what I'm trying to say here is essentially these two formulas, formula 1 and 2, they are totally independent of each other, you know. And this one, again, the first one just come from the basic definition of acceleration, while the second one come from the case that you can use the average velocity, which is the initial plus final divided by 2. And these two formulas, if you want, you can kind of memorize them. But again, you don't need to memorize them, but it's kind of simple. Well, as you see here, right, formula 3 and 4 are essentially derived using a formula 1 and 2, okay, by plugging something to get rid of some other quantities there, okay? So in this sense, if you only know these two formulas, okay, 1 and 2, you can solve all the problems, okay? But sometimes it's just a little bit more complicated because you need to solve, you need to get something first and then to get your final answer. Well, it's more convenient to use these two formulas directly in some problems, okay? And we'll definitely talk about some problem examples later on, okay? So anyway, just keep these two, keep these formulas in mind. Now, in the book, they summarize these formulas, I think in the end of the book, in the end of the chapter. Let's see. Where are they? Toward the end, like right before they gave the problems. Okay, I think it's here. Yes. See, constant acceleration motion, like this V formula and then delta X and then V. They use a little bit different notation than we did. I mean, they use VI, V naught for VI, and then a V for VF, but it's the same formula. Same thing here. I mean, they also only put T here, but essentially it's delta T is changing time, okay? Well, the last one here, they draw a little bit differently, but we had this, this one we draw like this. So what they did was they draw it like, essentially they draw like VF squared equals to VI squared plus 2A delta X, okay? Now you multiply 2A on both sides of this equation and add VI squared, you get this one. So it's just a little bit different way of writing, okay? And they didn't really provide this formula here. But as I said, you could, this formula is kind of important. You could derive the last two formulas using this formula, okay? Okay, any questions? Okay, let's try to, before we talk about any specific word problem that we want to solve, let's try to kind of go back a little bit and then kind of understand these two kind of motions qualitatively, okay? I think sometimes it's more important for you guys to understand what's going on qualitatively, okay, than quantitatively, than actually solving the problem. Actually, if you want to solve a word problem, you better understand the physics picture or qualitatively what's happening, you know? So let me use the PV, I mean, a space-time diagram to kind of explain this, okay? So let me first go back to the constant velocity motion, okay? As I said, this motion is really simple, almost trivial because just some same velocity going one direction all the time, right? So that means on the space-time diagram, you have something like this, a straight line, right? Remember, the reason it is straight lines is because the slope of the line gives you the velocity, and because velocity is constant, so certainly the slope is going to be constant, so you have straight line, okay? Well, it is also possible you have something like this, you know. this thing going down, right? Well, what's the difference? Okay, the difference here is, see, as time goes on, right? X going up, X is increasing, so this motion is going upward. Well, in this case, as time increases, X going down, so this motion going downward. So the direction of motion are different. Okay, in one case you have positive velocity, in the other case you have negative velocity. If you calculate the slope here, you get a negative number because the final position is smaller than the initial, so you get a negative number. So V is smaller than 0 here. Well, V is larger than 0. Okay. Now we can talk about the same thing for constant acceleration motion about using these diagrams. Well, it is simpler to start from the velocity versus time diagram. Because A is constant, right? See here, A is constant here. So the velocity is a change is constant. So that means the slope of this line is going to be constant. So for constant acceleration motion, you have, again, these two possibilities. Going velocity going either strictly up or strictly down, okay? Well, in both cases, the slope is constant. In this case, the slope is positive, so A is larger than 0. In this case, slope is negative, so A is smaller than 0, okay? So in this case, velocity is going up, this case, velocity is going down, okay? Well, certainly you have this as well, right? Okay, I guess that's enough. Okay, so let's go also to the space-time diagram for constant acceleration motion. Well, in this case, you do not expect that your diagram will be a straight line because your velocity is going to change. So the slope is not constant anymore, okay? So the formula, actually, as you can see from here, right? The displacement is proportional. I mean, there are two terms here. One is proportional to time. The other one is proportional to time squared. So correspondingly, if you plot X versus time, you get a parabola, okay? It could be all kinds of parabolas. For example, it could be something like this, or it could be something like this, you know? So basically, it's going to be more complicated, you know, like a parabola going like this corresponding case A is larger than 0. This corresponding case A is smaller than 0. Okay, but you're going to get some parabola here. Okay, well, because see the slope is changing, right? See in this case, the slope goes from negative to positive, so V increases, so A is larger than 0. In this case, the slope goes from positive to negative, so A is smaller than 0. Okay, so this all makes sense. Okay, so now, with constant acceleration, actually things getting a little more interesting. Okay. For example, let's consider some cases. Okay. For example, let's first consider one case. When you have a car here, you have initial velocity going to the right. Okay. Let's say the car got a positive acceleration. Okay. So acceleration going same direction. Okay. So what's going to happen to this to the motion? Okay, as we see here, right, because velocity is going to the right, certainly the car is going to move to the right. Now, because acceleration going to the same direction as velocity, right, so you have VF equal to VI plus A delta T. So certainly as time increases, the final velocity is going to getting larger and larger and larger. So basically what you observe here is going to be a car going to the right, but speeding up, okay, all the way, okay. So it's gonna, because the velocity is gonna increase linearly with acceleration like this, you know, it's just gonna go increase indefinitely, right? Well, that's impossible in reality, but that's what the constant acceleration tells you, right? So this is gonna speed up all the way, okay? Speed up all the way. So this actually kind of corresponds to the case when you kind of start your car, you know, start the engine, press the gas pedal, and then so your car start from 0 velocity and then start to pick up the velocity because of acceleration all the way to the velocity that you wanted. And then at that time, you would take your foot out of the pedal, and then your car probably, or we will keep it like a little bit loose so that it's going to stay with its constant velocity. Anyway, so that's like a speeding up process. Okay. However, let's look at another interesting case here. Okay. So in this case, you still have this car, and you got a velocity going to the right. But let's say this time you have acceleration going to the left. Okay. So what's going to happen for this car? Okay, think about it, right? So because acceleration going to left, so you have, say, basically you have a negative acceleration with a positive initial velocity. So certainly with this expression here, this term is going to become a kind of decrease, reduce the whole velocity you have here. So the velocity is going to decrease, okay? And it's going to decrease until it hits zero, okay? So slow down, okay? Slow down to zero velocity, okay? Now what's going to happen after it becomes, the velocity becomes zero? If you still have this acceleration, will the car stays there? Will the car stay there or what? What's going to happen? What do you guys think?
It's gonna stay there.
No. See, the problem is that because there's going to be acceleration, right? So it's not going to, yeah, it's going to go backward. That's more like it. See, you would think it's going to stay there, but no, because there's acceleration, right? With acceleration, the velocity is going to change constantly. Okay, so how can it change after you reach zero, right? But actually, okay, so the first part would be like it's going to stay here. I mean, sorry, it's going to reach here with v equal to zero, but after that, it's going to start to go backward. Okay, start because the acceleration. So at this time, your velocity becomes zero, right? So after that, this is still negative, right? So you're gonna get a negative number for the velocity. So this thing gonna start going back, okay? Well, how does the speed change when it goes backward? Because you have acceleration going in this direction, and then velocity going this direction as well. So it's actually gonna speed up going backward, okay? So we'll see, so it's gonna speed up here, okay? And it's gonna speed up all the way. So this is kind of like our first case. This is about our like kind of second case. So as we see here, right, this motion is actually a little more complicated, but it also means it's more interesting. So you can have like, depend on the direction of acceleration and direction of initial velocity, you could have totally different behavior, okay? This case, speed up all the way. Well, in this case, when the two are in the opposite direction, it's gonna slow down to zero and then going backward and speed up, okay, all the way. And while the second case may correspond to the case when you're driving on the road, right? You see a dog suddenly shows up on the right. So you press the brake pedal, right? And then your car stops, right? Well, in that case, there is an acceleration and then you stop zero. But after that, you don't see this part, right? Because that time, your car just stopped. There's no constant acceleration anymore because the engine already stopped, okay? There's nothing provided with this acceleration anymore. But so this part for the car is not very realistic. Okay? However, it is actually realistic in a different setup. That's what we're gonna talk about a little bit. Okay. So anyway, I want you guys kind of keep in mind this kind of picture, and then see the interplay between velocity and acceleration. You know, and then it can have different kind of motions depending on the direction of them. Okay. Do you have any questions? Okay, so we're done with this kind of, introduction of these two kind of motions. As I said, mostly the second motion, the constant acceleration motion, is the one that we're gonna spend time on because this one is a little bit non-trivial, you know, like you have some change of velocity and et cetera, et cetera. So it's better than this one, but it's also not too complicated, you know. So we'll solve some problems in about constant acceleration motion. In your homework, you'll see a lot of problems about this motion as well. Okay, so let's start from talk about an example. So the example we're going to do here is in section. Let's see. Okay, this one, section 2.5. Where is, okay, let's talk about this one, the Daytona 500, okay. I think that I don't know whether they resume it. I mean, this car racing had been suspended because of pandemic, right? I think NASCAR has been resumed, but I'm not sure about Daytona 500. You guys know about it? Okay. Anyway, I'm not a big fan of this anyway. So let's look at this problem. Okay, it's a very simple one. Okay, so you have a race car starting from the rest, accelerate at constant rate. Okay, so it gives you the acceleration, and then also it basically asks you the velocity of the car after it traveled this certain distance. Okay, and also the time it takes to go there. Okay, and then to calculate the average velocity. Okay, so again, the first thing we would do is we would okay. I mean, we would write everything down on on a piece of paper or starting from drawing a picture here. Okay, so let me see what is the okay example 2.4. Okay, example 2.4. Okay, so again, this is one-dimensional motion, right? So I'm gonna just draw this straight line here, and then draw the car here. And so the car is going speed. I mean, there's going to be an acceleration going this direction. Okay. So now let's specify what we know in this problem. Okay. So actually, there's already they draw it here as well. Okay. So what we know here is the acceleration is given as 5 point. So let me write it down here. So 5.00 meter per second square. Okay. Another thing we know is this thing starts from the rest, right? So the initial velocity is 0. So I'll write vi equals 0. Okay. Now sometimes it does not tell you explicitly something 0, but when it says start from the rest, it means the initial velocity 0. You need to read it out from your problem. Okay. Another thing we know here is the displacement, right? So say this is your displacement. I'm drawing terrible here. Delta x. Okay, and then let's define the positive direction going this way. Okay. So this is your origin. Okay. So the displacement is given. Okay. In the problem, it gives like something in feet. Because we want to work in this ISI unit, we need to convert it to meters. But this they already converted here for us. So I will just use this number, 30.5 meter. Okay. So that's the I don't know where this comes from. 3.5 meter. That's the displacement. Okay. So that's all the information we collect all the information we know from the problem. Okay. Let's see what is the unknown. So we want to know the final velocity. We want to know the time. We want to know the average velocity. Okay. So let me write it down. Okay. A, VF, B, delta T, and C, V average. Okay. Okay, so we got everything we know. We got the picture, we got the unknown, right? Now, before you try to connect them, try to picturize the fit this picture here, okay? So what's happening here? So you have a car starting from rest, and there's an acceleration pretty much given by the engine. Now, under this acceleration, certainly what's gonna happen is the car is gonna speed up from 0 all the way, like this, right? So, and then during this 30.5 meter, right, distance, right? Certainly, the velocity is gonna keep increasing, right, during this process. Okay, okay. Now, and certainly this is a constant acceleration problem, right? So now let's try to connect the unknown to the what is given in the problem. Okay, again, as I said, there's two ways to do that. One is starting from what is given to the unknown. The other one's starting from the unknown, see what we need. Okay, in this case, actually, it's not really that complicated. Essentially, as we know, there are 4 formulas here. Let me write them down again here. So you need to just choose one out of the 4 to connect them. So in this sense, it's kind of simple. Okay. Now, as I said, there's normally more than one way to solve a problem. Well, just some ways a little bit easier than the other. Okay. Okay, these are all we know about the constant acceleration motion. We have these four formulas, okay? Now, as I said, the point here is given those three pieces of information, we want to find out this one piece of information, which formula should we use, okay? As I said, there's normally more than one way to do it, but normally there is a shortest path to connect these together, okay? So based on what do you see here, what do you think, which one should we use to solve VF? Given A, VI, and delta X, which is the best way, best formula to use? You can send me a message, you know, telling me your choice. Okay. Okay, I got one response. Maybe anybody else? Okay, I got another response. Okay, so I got a couple of response here. Okay, so let's talk about it, right? Let's look at them. So how do we do this, right? I mean, there's always this method of exhaustion, right? You just go through them one by one, see whether this can be used. Okay, let's start from first one. Okay, so let's see the first one. Okay, it does have the unknown. That's good. Now let's see on this side, you have VI. Well, we know VI. You have A. We know, but there's delta T here, right? So delta T is the unknown. So this formula has two unknowns. Okay. So it's going to be hard for us to use this directly because there are two unknowns in this single formula. Okay, so let's look at the second one. Again, it has unknown VF. That's good. We do know VI, we do know delta X, but there's also this delta T here is unknown. So we cannot use this one. There's two unknowns here. Now, third one, it doesn't even have VF, right? So we cannot use this one. This one won't tell us anything about VF. Well, you could actually use, I mean, given VI and delta X and A, you could actually use this to get delta T, but that's not VF, right? So finally, we have this number 4 here. We want VF, and we know VI, we know A, and we know delta X. So we actually can use number 4 to solve the problem. So let's do that, okay? Okay, now there's two kind of ways to do it, okay? One is you start from the formula. Okay, this is about part A. See, the formula I give you is this, right? So if you want to solve for VF, is the unknown. You want to put the F on one side of it, everything else on the other side. So what you can do is multiply 2A on both sides. So I have 2A delta X VF squared minus VI squared, and then move this term to the left. So you have, in the end, you have VF squared equal to VI squared plus 2A delta X. Okay. So this is actually the way I prefer. Okay. So if you you're given the formula with all symbols, you manipulate this formula to get something that you have unknown on one side and everything else on the other side. So, and then, okay, VF here actually equals the square root of this whole thing, you know. And then you can plug in numbers right here, okay. So VI equals 0, so you have a 0 here, you don't have to worry about it. And then A is a 5 meter per second square. And then the delta X is 30.5 meter, okay? So plugs everything here. So you have, then you can use a calculator. So you have 2 times 5 is 10 times 30.5. And then take square root of that, okay? Let's see. So you got 17.5 meter per second, okay? Well, some of you may feel like this is too complicated. Another option for you guys is plugging numbers right away to this initial formula. So meaning that, okay, by the way, you can check the unit here, right? Meter divided by second square times meter. So you have meter square per second square, take square root, you got exactly meter per second. So as I said, another way to do it would be directly plugging numbers. So you have then from this, this is square, okay? Plug in number right here. So you have 30.5 meter equal to VF squared, okay? And then VI is 0, right? So minus 0, divided by 2 times 5 meter per second squared, okay? So this might be easier for some of you guys. As I said, I really want, I kind of hope you guys can do this because this is actually a more powerful way of solving problems. Using symbols directly here kind of will avoid mistakes, and then you can show some general relations between quantities. However, if you absolutely hate this kind of way of doing it, you can plug in numbers. If you really love numbers, you just have to leave these numbers. You can plug the numbers directly here. And then at this step, right, you could, it's maybe easier for you to see that. So VF squared equals to, this is a 10, right? So 10 meter per second squared times 30.5 meter, right? Now the same thing here, right? So you got the same answer. It's just a little bit different way to do it mathematically. Okay. Okay. After this one, let's do the second. Okay. Part B, which we want for delta t, right? Okay. Now let's do it together. So which one you think we can use to solve for delta t out of these four formulas? Again, send me a message. Okay. Okay. We got two answers so far. Again, just look at them. Again, this will be like something, a practice for you, you know. Okay, I got a couple questions. I mean answers, couple answers, like one or two. Actually, in this case, after you got your VF, right, it's actually, there's multi formulas can help us to get delta T. We can certainly use one because we know VI, we know A, and we got VF, and we can solve for delta T, right? And then second one, same thing. We have this delta X, we have VI, VF, we can get delta T. Actually, third one works as well because we have delta X, VI, and delta A. The only one that's not working is the last one because there's no delta T involved in the formula, so there's no way we can get it. So, and out of the three formulas, certainly we don't want use three because there's a square here, right? That means it's a quadratic equation. You have to solve the quadratic equation. It's a little bit more complicated. Although in this case, not too bad because VI is 0, so there's no linear term. But still, maybe either one of these two is good. So let's do the first one. Okay, so let's do VF equals to VI. Now, as I said, you could either manipulate the formula or you could plug in number directly. I would always do the first, you know. So for you guys, you can plug in numbers directly if you want to, but I'm gonna always do the formula first. Okay, so if you subtract VI on both sides, you have VF minus VI equal to A delta T. So delta T equals to VF minus VI divided by A. So in this case, we have VF, which is a 17.5 meter per second, and A is 5 meter per second, second squared. So as you can see, the unit here, meter per second divided by meter per second squared, give you nothing but second. 17.5 divided by 5. So you can just calculate that. 17.5 divided by 5. Okay. So got 3.5. So that's the answer for the second one. Okay. Now the third one, we want to get V average, right? Actually, the problem says you have two ways to get V average. Okay, so remember the basic definition of V average, okay, is this, okay? Total displacement divided by total time. This is true for any motion, okay? Well, certainly you can solve this one by, because you already got, you know delta X, you know delta T. So you can get this one by plugging 30.5 meter divided by 3.5 second, okay? Well, this is gonna give you, if you calculate that, it's gonna be 30.5 divided by 3.5, okay? So give you 8.71. Now, another way to do this would be using the formula we derived for constant acceleration motion only, okay? Now, as I emphasize, this one only works for constant A motion, okay? Okay, Now plug the numbers here. We have a 0 and we have a 17.5 meter per second divided by 2. So you got 8.75 meter per second. Okay. Well, you see there's a little bit difference between these two, but that's mostly because rounding issue. When we got these answers like this one, we rounded up, so we didn't keep all the decimal places. So they're essentially the same velocity. So both ways give you the same average velocity for the motion. Okay. Now again, as you see here, right? Because velocity keep increasing in this case, so the average velocity is somewhere in the middle between the initial and the final. Okay, you start from 0 and you end up with 17.5. The average is kind of like in the middle, 8.75. Okay. Okay. Do we have any questions for this one? Good. Okay. Let's see what time is what we have right now. Okay. Okay, we have about 20 minutes, so that's good. Okay. So after today, you can definitely solve all problems in chapter 2 homework. Okay. Well, we will do a little more exercise stuff maybe tomorrow because we cannot finish everything today. But you could, you could do the homework, okay, based on what we talk about. Again, for all the constant action motion problem, we just have these 4 formulas here. So essentially, you just need to find one formula that's the best, that works best for you. Okay, so. What we want to talk about right now, the kind of like the almost last topic here is the very specific kind of a motion, but it's also a constant acceleration motion. It's this motion, okay? It's a free fall motion. Remember, we talked about this motion in our introduction part when we talk about the what is physics, right? We use this as an example, right? You have 2 balls. Where's my baseball? Hello? Okay. So 2 balls, you drop them from the same height. One is heavier than the other. If you drop the same height, you get actually they actually fall to the ground at the same time. Okay. Okay. Now we kind of explained that there. Well, certainly that's under the condition that you can ignore the air resistance. But that's which is the case for a lot of cases. So let's talk about the free fall motion. Okay. Okay, so these what we learned here, we could try to explain why these 2 things, if you start from same height, it falls around same height. Okay. Now we would explain. Okay, we got 2 simple motions. Okay, one is the constant velocity motion. Okay, the other one is constant acceleration motion. Okay, actually it turns out for both motions, okay, you could say that if they start from same time, but they will reach the same distance, right? If they're doing constant velocity motion, or if they're doing constant acceleration motion. For both motions, we'll have this property. However, the question is, it is not a constant velocity motion. Okay, it turns out this is a constant acceleration motion. So my question for you guys is, why can't this be a constant velocity motion? Okay. So again, let me write it down here. Okay, so this is a constant acceleration motion. Why not a constant velocity motion? Okay, say if it is constant velocity motion, right? Because it's say it's the same distance. If they have the same constant velocity, then it will take same amount of time for them to travel, right? So it seems like it seems like it should be constant velocity motion, right? But why can't be? There's a simple fact that tells you this cannot be a constant velocity motion. It has to be a constant acceleration motion. Oh, I got a message. So because it's falling and not going up. No. See, if you say the constant velocity is going downward, right? Certainly it's going to fall, right? So that fact couldn't eliminate this possibility that it is a constant velocity motion. But there's one fact that will tell you it cannot be a constant velocity motion. Anybody else want to try? See, that's why I love the classroom. You know, in the classroom we can have some real discussion. Well, when we do it online, it's kind of really hard. You know. Nobody else? In the class, I will okay because of gravity. Yes, that's correct. But we haven't learned anything about gravity, so we cannot answer this question using dynamics. You know, we have to only answer the question based on kinematics that we learn, which is simply describing the motion with velocity and the acceleration. Okay. I guess well in the classroom I normally would point to somebody, try this, okay, but I don't want to do that in the online. You guys only have there are only 6 of you guys, and if I call your name, you may stop showing up next time. So maybe let me don't do that. So actually this cannot be a constant velocity motion. Why? Because look at the motion here, right? The key here is the motion starts from the rest, right? So see, I release the ball, let it go by itself. So if it is a constant velocity motion, right? Because at the very beginning, there's no initial velocity. It's constant velocity, the velocity is gonna stay 0. So this thing is gonna stay there instead of falling if it's a constant velocity motion, right? The fact that you see that this thing starts from the rest and then start to go down, it tells you it cannot be a constant velocity motion. There has to be a acceleration. Otherwise, you cannot move, you know, you cannot move at all, right? That makes sense to you guys? See, this is purely kinematics. I didn't talk about anything about gravity, where the acceleration come from, et cetera, et cetera. It's just based on the observation that this thing starts from the rest. So it cannot be a constant velocity motion, okay? So the answer is because start from the rest. Starts from the rest. Okay, so now we can understand this is a constant acceleration motion, and I can show you based on what the formula we get, why you can explain that by using this formula. So see you have 2 balls right here, and then they all go essentially they all go the same displacement, right? So you have del x1 and del x2, right? So these 2 are equal because they start from the same height. Now the question is, how do we are the 2 time change are the same or not, right? That's the question, right? So we assume that assume A is constant, okay? Basically, we're saying A1 equals to A2, okay? The expressions are the same for both of them, okay? So then, and we also know that the initial velocity, V1, VI initial equals to VI final, right? Equals 0 because we start from the rest. So there's no initial velocity here. So actually, if you look at the 4 formulas we got, this one, the third one actually is a good one to use in this context. So you have see delta x equals to vi delta t plus 1/2 a delta t squared, right? Okay, and as we see, this is 0 here. So essentially, we just have delta x equals to 1/2 a delta t squared, right? So from there, you can solve for delta t. If you multiply 2 and divide by a, and then take square root, you have delta t equals to 2 delta x over a, and then square root, okay? So this is the expression for the time in this, if we assume this is a constant acceleration. Now look, because are the same, A1 equal to A2, and delta x are the same, the displacement are the same, certainly you get the same delta t, right? So for A1 equal to A2, delta x equal to x2, based on this formula you have here, delta t1 has to be delta t2, okay? So they're the same formula. I mean, they're the same time, okay? So what we're doing here is we explain, if we assume x is constant, then the two balls gonna, if you start from the same height, they will reach the top bottom at same time. Okay, that makes sense. Now you may wonder, there's still two questions to ask, right? You may wonder why they moving with constant acceleration, right? Now we haven't talked about that part yet. That's a question of dynamics. Okay, I have to kind of explain where the motion come from. Okay, to answer that question. So we don't know that answer. Okay, so for now, the only thing we know is if we assume A is constant, then we can explain this phenomenon. Okay. Now another question you can ask is, are there maybe some other kind of motion that also satisfy this this condition? You know, maybe A is not constant, but A is changing with same rate for both the two objects as it goes down, right? In that case, it's possible that if you drop at the same time, they'll hit the bottom at the same time as well from the same height. Well, certainly that's possible, but that's a more complicated explanation. Okay. Now in physics, it's always the case that if there are two explanations to one phenomena, we'll always choose the simpler one. Okay, unless the simpler one does not work, then we go to a more complicated case. Okay. See, in this case, we try to explain this by constant velocity motion. It won't work because they start from the rest, right? So the next simplest explanation, it would be constant acceleration motion. Okay, so that's why we choose this one, because actually it works. There's no contradiction if you assume that. So we'll use that explanation. Okay, so in some sense, you may say there's some other possible theory to explain everything we have right now. Besides the theory we learned from this class, it's definitely possible, but those are going to be more complicated, and we will definitely choose a simple explanation. Okay, that's always the case in physics. Okay. So anyway, so this motion is actually quite important. Okay, it's so important that they give a special name for the acceleration in this motion. They call it G. Okay, so this is a free fall acceleration. Okay. We call G. Okay, and then G equal to 9.8 meter per second square. Okay, so this is a special number here. Okay, now you may ask again, where does this number come from? Well, when we do dynamics, I'm going to calculate and show you where this number come from. But for now, you just have to take it as somebody measured it, and it's 9.8. Okay, actually, we're going to have a lab this week to do this measurement ourselves. Okay, to measure this G. And so anyway, this is just a very important number. You don't need to memorize it, but after solving a couple problems in this chapter, it will stay in your mind. 9.8 is something like you'll probably remember forever. So I remember we talked about the acceleration, like I mentioned, like 1G, 2G, 3G, right? When they talk about acceleration in a rocket launch or acceleration of a roller coaster, and when they talk, they sometimes use G numbers. Well, these refer to this 9.8. So all these accelerations we have in our everyday life can be compared to this G to see whether it's large or small. Now you can feel this G by jumping out, hopefully not from a too high place. You know, I don't want to jump out from a 10th floor tower or something, but if you jump out from like a little bit like a ladder or something with like a maybe 1 meters high or 2 meters high, you can feel this acceleration. You know, that's a free fall acceleration you feel. Well, or you can feel it by taking a roller coaster when the coaster car's going like this. You know, it almost feel like it's a free fall. You know, so in that case you feel this acceleration again. Okay. Well, it's a or when you take elevator, you know, when the elevator is going downward, sometimes you feel part of it. It is a huge acceleration. It's going to definitely cause some damage, you know, doing that. But anyway, so this is a specific kind of a constant acceleration motion, and it's kind of a very important one for us. Okay, now this is another kind of free fall. I mean, we talk about so far the free fall is going down like this. Okay, another kind of free fall is if you toss the ball upward like this. Well, this whole process is a free fall as well. Although it doesn't look like that because at the very beginning it's going upward instead of going downward. But same thing, when this ball is in the air, if you can ignore all the air resistance, the acceleration is going to be the same acceleration, 9.8 meter per second squared. So even for this thing. So in problems, we'll do both this and this, okay? Actually, the tossing up part is even more interesting. So think about this, right? You toss the ball upward, it goes up, and it goes back, right? Think about this motion here, okay? So let's try to understand this motion a little bit qualitatively. At the very beginning, because you're tossing the ball upward, so you have initial velocity going upward, VI going up, okay? But remember, when you're in the air, there's going to be an acceleration going down, A, okay? Which is this 9.8. So what's going to happen, because these two going to the opposite directions, the ball is going to slow down, okay? And as it goes up. And then it's going to slow down, so all the way until the ball reaches zero. So when it reaches the highest point, the velocity becomes zero, okay? And it has to be, because if the velocity is not zero, it's going to keep going, okay? So at the highest point, the velocity becomes zero. But it's not going to stay there because there's acceleration. So after that, it's going to start to go downward, okay? And this thing going to start speed up downward, okay? This is very similar to the case we talk about here, see? Well, as I said, in this case, it's a little bit unrealistic to see this something going backward with speeding up. But actually, in the case of a free fall, it is actually realistic and very realistic because you can do it almost like every day, right? See, it goes up. See, whenever these two going opposite directions, you know, slows down, reaches zero, and then going backward, speeding up. Okay, this is exactly what's happening here. Okay. It's pretty amazing, right? So, actually, this is that case. Okay, so after we discuss this, we're gonna we need to do an example on free fall motion to calculate something, and then I'm gonna give you guys a exercise to do in class to kind of get familiar with everything we learned. So, but we're running out of time today, so we'll do it tomorrow. So today we finished a little bit early, like 3 minutes early. I think that's good, you know. I hope we can do more like that, okay? So let's stop right here.